Hi all, today we will discuss about memory hierarchy and the different memory device, different characteristics of the memory devices. So first it is required to understand what is the importance of having memory hierarchy in computer system. Remember in computer system design, as you might have already known, there are different types of memories exist in the computer, and this is just to enhance the organizing of memory, such that the goal here is to minimize the access time and reduce the cost of memory devices. So memory hierarchy was developed based on a program behavior known as a locality of reference. So if somebody asks what is the requirement for having different kinds of memory, that is called memory hierarchy in computers, means the goal is to minimize two parameters. One is access time. The minimizing the access time means whatever the data that is required by the processor, that is CU, ALU and register, should be readily available in less amount of time. That is the meaning of access time. And at the same time, just to satisfy the goal of access time, we can't keep the high cost memory, which is like main memory and registers. So there should be a balance between access time and the cost. And there is another reason behind having hierarchy in computers is a famous principle called locality of reference. So it is really necessary to understand the concept of locality of reference. What locality of reference is means, when you refer a memory word in a memory and you expect that, it is a simple expectation that then the next word should be can be accessed by a processor in near future. Let me explain it. If this is my memory and it is divided into four parts, these are the addresses of the memory. Now I am accessing a memory word at memory location 1, address 1. Then it's a natural tendency that next we may access 26. So with an expectation of accessing the next element 26, we keep the 26 in the fall. Let's assume this is main memory and this is cache memory. When the CPU makes a request to access the memory element at memory location 1, then it is natural expectation that we would access the next consecutive next element, that is 26. With this expectation, we transfer or we move the 26 word to cache memory so that it is readily available by the processor. So the total cache memory or the total memory hierarchy works based on this principle, that is called locality of reference. So a memory hierarchy was developed based on a program behavior known as locality of reference. And also there are certain properties of the memory, such as capacity. It is the global volume of the information the memory can store. As we move from top to bottom in the hierarchy, the capacity increases. Next is the access time. It is the time interval between the read-write request and availability of the data. As we move from top to the bottom, the hierarchy, the access time increases. So in design of the computer systems, so first it is really important to understand the need for memory hierarchy, and we came to know that the access time, the reason for having different memory devices in a computer is that to increase the access time, and at the same time that we should reduce the cost, and it should follow the principle of locality of reference. Still there are some more points needs to be discussed about the need for memory hierarchy. In a design of the computer system, a processor means it is a combination of CU, it is a combination of, whenever you refer a word processor, remember it is a combination of control unit, ALU and registers. So these three together we refer as a processor. So in the design of a computer system, a processor as well as large amount of memory devices has been used. However, the main problem is these parts are expensive. This is very important term. You can't keep the main memory for 1 TB. So in general, when we speak about computer configuration, we say RAM is of 4 GB, 5 GB or 8 GB. So why can't you keep the RAM as 1 TB? Because it is quite expensive. So the need for having secondary memory, that is hard disk of 1 TB or 2 TB, is that just to minimize the cost of the memory hierarchy in computer. So we can't keep the RAM of capacity 1 TB because it is quite expensive. Remember when we discussed about memory devices, RAM is made up of semiconductor devices which are expensive when compared with the hard disk manufacturing technologies like magnetic disk and magnetic tape or optical disk. So these parts are expensive. So the memory organization of the system can be done by a memory hierarchy. The low cost memory volume should be high, high cost memory volume should be low. This is the simple logic. Next, it has several levels of memory with different performance rates. Having different levels of memory with different performance rates. So the performance of a register is higher than the performance of the cache. Similarly, performance of a cache memory is higher than the performance of main memory. But all these can support an exact purpose such that the access time can be reduced. So this is the point very important. The goal of having memory hierarchy is that, as we discussed in the previous slide, we should reduce access time and cost of the memory. This is the goal of memory hierarchy, is to reduce access time, at the same time reduce the cost. The memory in a computer can be divided into 5 hierarchies based on the speed as well as use. The processor can move from one level to another based on its requirement. So what are the different levels of hierarchies in the memory? Means one is register, These are also called CPU registers. Next is cache memory. Next is main memory. Next is secondary memory, which is made up of magnetic disk, magnetic tape, and optical disk. So this is a pictorial representation of memory hierarchy. So in that, the highest level is the memory registers. Next is the cache memory. Next is the main memory. Next comes secondary memory or auxiliary memory. These two can be referred as auxiliary memory. See, if you look at the pyramidal structure, it says that the volume of the CPU registers is lesser when compared with cache memory, and when it goes down from register to cache memory to main memory to auxiliary memory, that is magnetic disk and magnetic tape, you can observe that the capacity, the amount of data that can be stored is getting increased. Memory capacity is getting increased if you go from top to bottom of the pyramid structure. The reason why we have taken pyramid, it exactly resembles the memory hierarchy in a computers. If you go from top to bottom, the amount of capacity, storage capacity, is getting increased. That means the amount of data that you store in a register is lesser when compared with the amount of data you store in a cache memory. The capacity of main memory is greater than the capacity of cache memory. So likewise, when you go from top to bottom, the capacity of different memory elements is getting increased. Similarly, if you look at the access time, which was the main goal of the having memory hierarchy, the access time, if you go from bottom to top, it increases because the CU and ALU, which you can together call as a processor with some special purpose registers, for which memory element is very near to processor means register. So the access time is definitely low. Next, when you compare with a cache memory, the is little bit access time is little bit increased. So by this way, what's happening, the access time is very high when you go to bottom. It is very low when you go to CPU registers. Next, look at this picture. It also has got the same memory hierarchy: CPU registers, cache memory. Next, we have main memory and magnetic disk, optical disk, magnetic tape. So these are called different memory at level 0, level 1, level 2, level 3, level 4. Total 5 levels of memories. And if you look at the cost of the CPU and registers is higher when you compare with the cost of the magnetic tape. So it has got low cost it has got high cost. So the cost is getting increased from bottom to top. Next, if you look at the capacity, as we discussed, capacity is getting increased from top to bottom. Similarly, access time is also getting increased from top to bottom. So remember, the goal of memory hierarchy is that you should have less access time. For that we have different levels of hierarchy. See, if our goal was only to reduce the cost, you can keep only these three memories which are cheaper, secondary memory. It's not required for having these the first three levels. If your goal is to just reduce the cost, because these magnetic disc, optical disc, and magnetic are cheap when you compare with the CPU, cache memory, and main memory. So it's really necessary to understand that access time and capacity is getting increased from top to bottom. Capacity is anyway is getting increased. Similarly, access time is also getting increased. But our goal is to reduce the access time. For that, we have registers. See what happens when the user enters the data that goes and store in any of these secondary devices. So as and when it required, it moved to main memory, and from main memory to cache memory, it is required based on the principle of locality of reference, and from cache memory it is moved to registers so that the access time gets decreased. So remember, the cost is decreased from top to bottom, but similarly the access time is getting increased from top to bottom. It is getting increased. Similarly, capacity is also increased from top to bottom. So this is about memory hierarchy design in computers. Next, we know that the primary memory is also known as internal memory, and this is accessible by the processor straightly. That means the processor can have a direct communication to all these memory hierarchy elements which belongs to primary memory, and this includes main memory, cache, and CPU registers. So you can divide this memory hierarchy picture into by two parts, and one, the primary memory elements, which has direct access by the processor. Processor can communicate directly with these memory elements. Secondary memory is also known as external memory, and this is accessible by the processor through input and output mode. This memory includes the magnetic tapes, magnetic disk, optical disk. So this is one way of classifying the memory hierarchy elements. Next we see some characteristics of the memory. Now let us discuss characteristics of the memory. So the memory hierarchy characteristics, there are so many characteristics in which one of the important one is performance. That is, previously the designing of a computer system was done without memory hierarchy, and the speed gap due to which the speed gap among the main memory as well as CPU registers enhances because of the huge disparity in access time, which will cause the low performance of the system. So the enhancement was made mandatory. The enhancement of this was designed in the memory hierarchy module due to the system's performance increase. So performance is one of the main characteristics of the memory which can affect the overall computer system speed. Next we have the ability. The ability of the memory hierarchy is the total amount of data the memory can store, or it can also be called capacity. So the ability of the memory hierarchy is the total amount of data the memory can store. Because whenever we shift from top to bottom the memory hierarchy diagram, inside this memory hierarchy, then the capacity will increase. So the capacity of a CPU registers is much lesser than compared to the capacity of the secondary memory. So this is the second characteristics of the memory devices, that is the capacity. And the third one, the most important one, is the access time. So we should discuss in detail about access time, because the access time in memory hierarchy is the interval of the time among the data availability as well as request to read or write. So try to understand the access time. That in general, access time means the time required to access a memory word. And when you say the access with respect to memory, we have two operations, read and write. So the access time for read operation is different from the access time from the write operation. The amount of time required to access a word is definitely not going to be the same as the access time required to perform a write operation. Then what is the definition of an access time in general means? The access time in a memory hierarchy, that means this access time, this definition is applicable to all the different levels of memories in the memory hierarchy. The access time in memory hierarchy is the interval, that means the gap, the interval of the time among the data availability. Because the data, if you want to perform a read operation, the data should be available in the memory first. So the moment the data is available from the memory as well as the request to read or write, when you complete a read request, the amount of time required to complete the read request operation, or the amount of time required to complete the write request operation, this amount of time, this duration is called access time. Because whenever we shift from top to bottom inside the memory hierarchy, then the access time will definitely increase. We'll discuss some more points about access time in practical. So the access time for RAM means from main memory or cache memory or registers, the time to address the unit and perform the transfer. What is the meaning of time to address the unit? The time the content of the PC register is loaded to MAR. From that moment, the count of access time starts. Remember, when you want to access a word, that address is present in the PC. From that, it has to be loaded into a special register called MAR. So this time onwards, it is counted as access time. So the time to address the unit, that means once you load the address of PC to MAR, and go to main memory RAM and find out the address present in this MAR and fetch this and place the word some 12 let me be in MDR. This amount of time is called the read. For RAM, the time to address the unit and perform the transfer. Transfer should be performed. Read operation should be success. When you say read operation is success, once the data is loaded into MDR, till the time it is called the read operation. Once the data has been loaded into MDR, the amount of time for read operation or read operation is finished. The execution of the read operation is completed because the data is readily available in the memory data register. Remember, MAR and MDR, the two are the two special registers which deals with the memory read operation and write operation. MAR stands for memory address register and MDR stands for memory data register. And the same definition of access time slightly changes for secondary memory. The time to position the read-write head over the desired location. It's really important to understand how access time is defined for the case of secondary memory. Remember, secondary memory is made up of magnetic disk, magnetic tapes, or optical disk. If these are the magnetic disks, let's assume, and there is a read-write head, this is called read-write head, which can move across each disk in the magnetic. This is called secondary memory. So in this case, what's happening? How can you define access time in this case means for non-random access memory such as magnetic disk, the time to position read-write head over the desired location. That means, see, this is called a disk. This disk contains tracks or this disk contains some uh, tracks, and these tracks are further divided into location. If this is one magnetic disk, you can also call cylinder, and these are called tracks. These tracks are divided into different location, so this is called one memory location. Now it is the job of read write head. Now the amount of time the to position to place this particular read write head onto the desired location. See, if you want this memory location, the read write head should be placed here. So from that time onwards, time required to read the data on this particular location and place it in registers, this duration is called access time in case of secondary memory devices. So let me explain once again. The access time for primary memory devices such as main memory, cache memory, or register is a simple. The time to address the unit, we should find out the address of the memory location. We should find the particular memory location in the memory and perform the read operation and write operation. This amount of time is called access time for the main memory devices. But in case of secondary devices, it's not just finding the address, the time from which the read write head, is used to read or write the data in secondary memory. The time to place this read write head on the desired memory location, on the required memory location. From this the transfer happened. Then the transfer happens once you place read write head, right? Maybe read operation or write operation. This total time is called access time.
and it plays a very key role in memory devices. This access time, the goal of the access time should be low, as we know. For that, we have different memory hierarchy levels in a computer. And another important characteristic is called memory cycle time. The memory cycle time is that access time plus any other time required before second access can be started. It's really important to understand the cycle time. See, let's assume there are two memory read operations. So when you require two memory read operations, first you place the address in MAR, and now the time starts. Let's assume this is access time. Once you place this MAR, go to memory and perform read operation or write operation. So this is called one memory read operation. Next, we need two consecutive memory read operations. Now it takes some time. Again, another second memory read operation starts. So what is this time is required for? Just to organize the memory elements internally. Some internal organization. So in case of two consecutive memory read operation, the next read operation doesn't start immediately when the first memory read operation finishes. There is some time lapse. There is some time gap between the two consecutive memory read operations. Now let us see what is this time gap. What is the requirement for this having time gap? See, once you read a word from the memory and place in the MDR, from MDR to concerned registers, now it is required to place the address. Now the PC should be loaded. Let's assume PC is also loaded with the second word address. Now this address has to be loaded into MER because the access time starts once the address is loaded in the MER. But there should be a time gap. It takes some time to load the address from PC to MER. Like that, there are some internal organizations from some operations are required before starting the next or second memory read operation. So this gap plus access time, total called cycle time. So if you define a cycle time is access time plus some time gap. You can call it a small data, so delta t. If this is t, this would be very small with respect to t, delta t, but it also plays an important role. So this time is called as cycle time. And another important memory characteristic is the transfer rate. The data rate are called transfer rate. Is the rate at which data is transferred to and from the memory devices. So what is the meaning of the rate at which the data is transferred? So remember, whenever you deal with the word rate, it is related with time. The rate, that means you can also refer as speed. How can you measure the speed in terms of time? Like I can transfer some 1 million words in 1 nanosecond. So it is with respect to time. You are defining the data transfer rate. The rate at which the data is transferred to and from memory devices. That means, in general words, in 1 minute, how many read operations or write operations can be performed? Not complete read operation, just the data has to be transformed the memory devices. The data is be transferred to and from memory devices means the amount of time required to read the data and place in MDR. This is for read operation. Similarly, the amount of time required to place MDR data to memory. This is called for write operation. So let us take it takes 10 seconds for performing, or 1 second for transferring the data from MDR to memory, or from memory to MDR. The both will not be same, of course. Then you take the average time. Let's assume that average time is 1 second. Then how can you measure the speed? In 1 minute you can send 60 words. So 60 words per minute, or 1 word per second. This is called the data transfer rate. How can you measure? Simple. For random access memory or for main memory, this is nothing but 1 by cycle time. Remember, cycle time is nothing but access time plus some extra time required to perform some internal organization. So this is about definition of data transfer rate for uh, main memory elements such as registers, cache, and main memory. And the data transfer rate definition for secondary memory devices such as magnetic disk or magnetic tape or optical disk is slightly different. For non-random, because we have a read write head to uh, perform read operation and write operation. For non-random access memory, this data transfer rate is Tn is equals to Ta plus n by r. Tn is the average time to read or write n bits. Average time required to read or write n bits. Here n stands for number of bits that you want to read. Is equals to average access time. Average access time for both read and write. So remember, the access time for read operation and write operation would not be the same. So take the average of that average access time. So access time means, in case of non-random access memory, what is the definition of the access time? The time to position the read-write head on the desired location. From that point onwards, the counting of access time starts. So the average access time plus how many number of bits divided by data transfer rate. The data transfer rate in bits per second. Then let's assume uh, I have some 100 bits. How can you transfer how much time is required for, and its data transfer rate is, its capacity is 10 bits per second. The device capacity is it can transfer only 10 bits per second. 10 bits per second. So what happens? How much time is required to transfer 100 bits? 10 seconds. How would you get 10 10 jar bits cancel, 10 seconds. So the transfer rate depends upon how many number of bits are required to transfer, and what is the data transfer rate, that is called bits per second. So in this example we take that the capacity of this data transfer rate capacity of this magnetic device or secondary memory device is 10 bits per second. It can transfer at the max 10 bits in 1 second. But I want to transfer 100 bits. Then how much time it takes means obviously 10 seconds. 10 seconds plus for transferring each bit, say on an average you take 10 seconds for transferring that, plus average access time. Maybe it's the read operation or write operation, right? What is the time required to access time means the time, the point of time at which the desired read write head is placed at a desired location, that time, and the number of bit, the amount of time required to perform read operation or write operation. So this is called average time to read and write n bits. So this is for the case of non-random access memory. Next, the another important character is permanence of storage. Permanence of storage. What it says, some memories lose information over a period of time. So even when you say the memory, in this you should remember the important characteristics of the memory, that is volatility. We said volatility means losing the data in case of power failure. The data is not going to be stored if you say volatile. And you know that secondary memory is non-volatile, that is permanent. Though we are calling secondary memory as a permanent memory, in general memory lose the information over a period of time, maybe because of the dust particles or frequent read and write operations. So there are different reasons for the memory losing the information over a period of time. For example, there can be some memories where the stored data bit value, what is the meaning of losing the information means, there can be some memories where the stored bit value 1 loses its strength and to become 0 over a period of time. So that is the meaning of losing the information. That is, you stored 1 in the memory, but over a period of it is becoming 0. It loses its strength. 1 loses its strength and becomes 0. This is nothing but losing the information over a period of time. So these kind of memories require refreshing. So the solution is refreshing. The memories which require refreshing are termed as dynamic memories. In contrast, memories which do not require refreshing are called static memories. So the dynamic memory means it will lose the information over a period of time and you require a technique called refresh. Refresh is required for dynamic memories. And static memories are the memories which don't require refreshing. Another factor which can destroy the contents is the presence and absence of electricity. The memories lose their content on failure of power are termed as volatile memories. Those which do not are called non-volatile. Magnetic memories are non-volatile and semiconductor main memories are volatile in nature. So this property permanence of storage, what it says, with respect to over a period of time, the memory devices may lose its information. Losing the information here means 1 becomes 0 and it becomes a weekend. When 1 loses its strength, it becomes 0. So the solution is it requires some refreshing. Such memories are called dynamic memories, which require refreshing. But there are also static memories, such as cache memory, which don't lose the data, which doesn't require refreshing. This is one aspect, losing the information over a period of time. And the other aspect is that losing the information with power failure. This we know already. Such type of memories which lose the data over the power failure is called volatile. And all the main memory elements such as main memory, cache memory, registers are volatile in nature. Those which do not lose their memory with power failure, that property is called non-volatile. And the examples for non-volatile memory are auxiliary memory or secondary memory devices such as uh, mem- volat- semiconductor such as magnetic disk. And these are the advantages of having memory hierarchy. Memory distributing is simple and economical, removes external destruction, data can be spread over all, permits demand paging and pre-paging, swapping will be more proficient.